it flies in total silence. No radar warning, no visible trace. By the time anyone knows it's there, it's already completed the mission. This is the B-21 Raider, the newest bomber in America's arsenal, designed to operate where no other aircraft can. It's built to sneak past the most advanced air defenses and hit its target with pinpoint accuracy. In this video, we're stepping through the interior of the B-21 to understand how every system, from the cockpit to the payload bays, works together to make it one of the most formidable aircraft ever built. But here's the catch. Almost nothing about the B-21 has ever been revealed. Every detail you'll see is built on theories and speculation, and along the way we'll uncover a detail in its design that could change the balance of power in the skies. The heart of any bomber is its cockpit, and the B-21 Raiders is unlike any seen before. It's designed for efficiency and comfort and shows how the cockpit is a masterpiece of modern avionics and ergonomics. The crew compartment has been designed with the success of each and every mission in mind. The B-21 cockpit is equipped with the latest glass cockpit technology. Instead of a traditional array of dials and buttons, the cockpit consists of high-resolution touchscreens that integrate various control systems into one centralized interface. These displays allow the crew to easily monitor flight systems, weapon status, navigation, and more, all in real time. With this design, the B-21 crew can rest assured that they can access data critical to the mission quickly and efficiently without having to worry about unnecessary distractions. The avionics suite automates much of the routine operation and reduces the workload for the crew. For instance, the bomber's navigation system works seamlessly with the mission planning software. But what does this mean for the mission? It allows for dynamic route adjustments as needed based on real-time data. So whether the B-21 is flying over hostile terrain or long stretches of ocean, the advanced avionics will ensure that the aircraft stays on course and still be able to maintain its stealth and fuel efficiency. The B-21 Raider is a highly automated aircraft, and this plays a huge role in reducing the crew's operational burden. With traditional bombers, manual inputs for most flight functions have to be given, but the B-21 takes that entire stress away. It integrates autonomous systems that can control many aspects of the flight. The automation helps the crew to focus on high-level mission tasks rather than on piloting the aircraft itself. Beyond the cockpit, the interior of the B-21 is designed to optimize both stealth and mission flexibility. While much attention has been given to its aerodynamic shape, the interior components are just as important in defining the B-21's capabilities. The B-21 Raider's payload bay is definitely one of its most innovative features. Unlike traditional bombers that carry bombs on external hardpoints, the B-21 houses its munitions in internal bays that are integrated into the fuselage. This reduces the bomber's radar cross-section so the aircraft can still maintain its stealth profile. The payload bay is spacious and designed to hold a range of munitions, from precision-guided bombs to nuclear payloads. This internal design makes it so the aircraft is able to carry large payloads without once compromising the aircraft's low radar visibility. The electromechanical systems in the bay have been designed with quick deployment in mind, so that the crew is able to drop munitions efficiently when the time comes. The modular nature of the B-21's payload system means that it can be customized for different mission types, whether it's a conventional strike or a nuclear deterrence mission. This adaptability makes the B-21 a flexible and highly effective tool in long-range strategic bombing. If you like this video so far, make sure you hit the thumbs up button, subscribe to the channel, and let us know in the comments what bomber you would like to hear about next. While most people think of stealth in terms of an aircraft's shape or coating, the B-21's interior is just as important to its low radar signature. The aircraft is equipped with radar-absorbing materials that are integrated into its airframe and internal components. These materials help prevent the B-21 from reflecting radar waves back to enemy systems, effectively blinding enemy radar. They help keep the B-21 undetected, even in areas with advanced ground-based radar or airborne radar platforms. These materials also contribute to the bomber's stealth in the infrared spectrum, because they help to reduce its heat signature and evade infrared detection. Also embedded in the B-21 are advanced electronic warfare systems that provide a significant advantage in the electromagnetic spectrum. These systems help the bomber jam enemy radar and interfere with communications to further enhance its survivability. The interior of the B-21 includes systems that can disrupt and deceive enemy defense systems to create a layered defense that is hard to counter. These electronic warfare systems work in tandem with its stealth design to create a near-impenetrable defense system. The advanced electronic capabilities are a key component of the aircraft's ability to operate in highly contested environments without being detected. Fuel efficiency is a crucial component of any bomber's design, especially one that is built for long-range operations. The B-21 Raider takes a unique approach because it integrates its fuel storage system directly into its internal structure. This maximizes the internal space and also reduces the need for external fuel tanks. By integrating it this way, it not only keeps the bomber's radar signature low, but also helps the aircraft achieve longer flight durations without sacrificing operational efficiency. The bomber can fly over 6,000 miles without needing to refuel, making it a truly global asset for long-range strike missions. When paired with aerial refueling, the B-21 has virtually unlimited range. Can you imagine that? This means it can travel across oceans or strike deep into enemy territory without ever needing to rely on forward bases. The B-21 Raider is also a very fuel-efficient design, which makes it an ideal choice for strategic missions. Its wing-body blend ensures that the aircraft can achieve high levels of aerodynamic efficiency while also carrying a full payload of munitions. This combination of stealth and fuel efficiency allows the B-21 to conduct precision strikes without needing to make multiple refueling stops. The B-21 Raider was designed with long-term sustainability in mind. The aircraft's internal systems are modular, which means they can be easily upgraded or replaced without requiring significant downtime. This modularity extends to its payload systems, which can be adapted based on mission requirements. This feature ensures that the B-21 can be continuously upgraded to keep pace with evolving military needs and technological advancements. The B-21 also comes equipped with advanced self-diagnostic systems that help identify issues before they become problems. These systems monitor the aircraft's performance in real time and check for any structural or system malfunctions to alert maintenance crews when issues arise. This proactive approach minimizes downtime and makes sure that the bomber remains operational for longer periods. Before we go ahead, how do you think the future of military aircraft like the B-21 will change with the rise of cyber warfare and digital threats? Let us know in the comments below. The crew life support systems inside the B-21 Raider are designed to ensure that the crew remains comfortable during long-duration missions that can last up to 12 hours or more. The bomber operates at high altitudes, so maintaining proper oxygen levels and environmental control is crucial. To achieve this, the aircraft is equipped with advanced systems that regulate the oxygen supply and maintain the pressurized cabin for optimal breathing and comfort. These systems are finely tuned to provide a consistent supply of oxygen, ensuring that the crew can function effectively even in the challenging conditions of high-altitude flight. The B-21 also features an advanced air filtration system that keeps the interior air clean and free from harmful contaminants. Given the extended nature of its missions, the aircraft also employs temperature regulation systems. The cockpit temperature can fluctuate drastically at high altitudes, but this is adjusted to keep the crew alert and ensure that all sensitive equipment in the cockpit remains at operational levels. In the event of an emergency, such as sudden cabin depressurization, the B-21 is equipped with emergency oxygen masks that deploy automatically to make sure of the crew's survival, even if the primary systems fail. The redundant systems built into the aircraft offer backup solutions. These features make the B-21 one of the most crew-friendly bombers, designed not just for combat effectiveness but for crew safety during prolonged and potentially high-risk operations. Inside the B-21 Raider lies a world of advanced systems. Every component of this aircraft is carefully designed to ensure maximum efficiency and operational effectiveness. As the U.S. military prepares for the future, the B-21 Raider stands as a symbol of what is possible when innovation meets operational excellence. Two giants, one rivalry. We're talking about the Airbus A380 and the Boeing 747. Both have changed the course of aviation forever and stand as legends today. But the real story isn't in their size or fame, it's their wings. Vast structures that do more than keep the aircraft flying. They explain why one of these aircraft survived and the other vanished too soon. The Boeing 747 first flew in 1969. At the time, jet travel was booming and airports were crowded. Airlines knew they wanted something revolutionary. Boeing gave them a wide body with wings spanning 195 feet that was capable of flying over 5,000 miles nonstop. For its era, the 747's wing was an engineering marvel, designed almost entirely with wind tunnels and hand-drawn calculations. Fast forward to 2005, Airbus unveiled the A380 with wings stretching nearly 262 feet across. Unlike the 747, these wings were built in the computer age using advanced simulations and composites. They weren't just for the present. Airbus deliberately designed them to support a future stretch version, the never-built A380-900, which could have carried over 900 passengers. That ambition shaped everything about their size and strength. On paper, the A380 dominates. Its wing area is over 9,100 square feet compared to the 747-400's 5,500 square feet. Each wingtip of the A380 towers higher than a three-story building when parked. With this sheer scale, the A380 can generate enough lift to carry more than 1.2 million pounds into the air. The 747's wings, though smaller, were designed with stricter limits. Boeing engineers had to keep the span below 200 feet so it could fit into existing hangars and taxiways. That restriction forced them to prioritize efficiency. This created a wing that balanced range and capacity. Bigger wings can mean more lift, but they also bring problems like more drag, weight, and eventually cost. Airbus went big because it believed hub-to-hub super jumbo travel was the future. Boeing kept things moderate, betting airlines wanted flexibility. The difference in wing size reflects the very strategies that shaped their destinies. Quick question before we move on. Which giant do you think had the better start, Boeing's 747 or the A380? Let us know in the comments. And if you like this video so far, don't forget to subscribe to the channel. The 747's wings were largely aluminum alloy, built with 1960s technology. Later updates added composites and secondary structures, but the core remained traditional metal. The A380's wings, built in Broughton, UK, are a mix of aluminum and advanced carbon fiber composites. Entire trailing edges are carbon reinforced. Each wing weighs around 40 tons empty and was so large it had to be shipped by barge and special transport convoys across Europe before final assembly in Toulouse. If you have ever seen a 747 liftoff, you'll have noticed that its wings arch upwards several meters. That flex isn't a weakness, it's strength. It's how aluminum absorbs turbulence and redistributes stress. Pilots often describe the 747's wing flex as alive, a graceful movement that reassured them the aircraft was working with the air, not against it. The A380 takes this even further. During heavy loads, its wings can flex upwards by nearly 7 meters at the tips. Airbus achieved this by blending metal with carbon fiber composites, which made the wings lighter but also incredibly flexible. This flex smoothed turbulence so effectively that passengers often describe the A380's ride feeling like gliding on rails. Flexibility is why these wings last for decades and can endure takeoffs, landings, and the stress of unpredictable weather storms without cracking under strain. The 747's wing sweep is about 37.5 degrees, ideal for cruising near Mach 0.85. Early versions had no winglets, but in the 1980s, Boeing added them to the 747-400, cutting down drag from wingtip vortices. The later 747-8 went even further by replacing winglets with elegant raked tips and a recontoured airfoil. This gave it a lift-to-drag ratio comparable to modern twin jets. The A380's wings are less swept, around 33.5 degrees, and also much broader. Instead of winglets, Airbus used upward curved wing fences. Engineers debated using raked tips like Boeing's, but the sheer span of the A380 made fences more practical for controlling turbulence. Despite their different solutions, both designs achieved efficient long-haul cruise. The A380, despite being heavier and larger, manages fuel burn per passenger close to the 747-8. The 747 relies on a remarkably complex high-lift system for its time. Along the leading edge are 14 Kruger flaps and triple-slotted flaps on the trailing edge. In full landing configuration, the 747's wingspan visually grows and increases both surface area and curvature. Pilots have described the drag from these flaps as so immense that it feels like throwing an anchor out of the cockpit. But this mechanism allowed a 400-ton aircraft designed in the 1960s to land at speeds manageable for major airports. The A380's system takes that complexity to a higher level. Its leading edges use full-span slats which extend smoothly to reshape airflow. On the trailing edge, Airbus added huge flaps working alongside drooped ailerons, so even the roll control surfaces assist in generating lift during takeoff and landing. The flaperons are hybrid surfaces almost the size of a regional jet's wing that blend the function of both flaps and ailerons. At full extension, the A380's wing area increases by nearly 40%. Few passengers notice, but these hidden transformations are the reason these giants can rise gracefully from runways rather than needing impossibly long airstrips. The A380 also features one of the most advanced fuel management systems ever installed on a passenger aircraft. Its wings contain multiple tanks and fuel is actively moved around mid-flight to adjust the aircraft's center of gravity and relieve bending stresses. This wing bending relief system means less fatigue and lower maintenance over the years. Each A380 wing can carry over 250,000 liters of fuel. Airbus engineers joke that the A380's wings fly with fuel twice, because once to power the engines and then once to balance the structure. The 747 also uses wing tanks, but its system is simpler. Fuel distribution there is primarily for balance and trimming the aircraft's nose attitude and not for reducing wing stress. For its time, it was advanced, but the A380 turned fuel into an active tool of structural management. It's one of those invisible differences that most passengers will never know, but one that highlights just how much wing design evolved over 40 years. Passengers often describe the A380 as the smoothest ride they've ever felt. Its massive wings lower wing loading, meaning each square meter of surface carries less weight. Combined with flex and active gust load alleviation from fly-by-wire controls, the turbulence feels muted. The 747, with its higher wing loading, reacts more sharply. For some, this makes it feel more real, like a machine responding dynamically to the air. For others, it means bumpier rides. The difference comes directly from the wings. One is calm and ship-like, the other lively and bird-like. Both unforgettable in their own way. Boeing deliberately capped the 747's wingspan under 200 feet because of infrastructure to ensure it could fit into existing hangars and gates. Otherwise, airports would have had to spend millions in upgrades. That decision alone gave the 747 a huge commercial advantage. Airlines didn't just buy a plane, they bought global access. The A380 broke that convention with a wingspan of 262 feet. Suddenly, regulators had to create a whole new category, Code F, for super-wide aircraft. Airports that wanted the A380 had to widen taxiways and reinforce runways. Singapore Changi, Dubai, and London Heathrow spent heavily to welcome the jet, but many airports didn't. In the United States, only a handful of airports like Miami, JFK, and LAX upgraded to handle it. Others simply couldn't justify the cost for one aircraft type. This meant that, ironically, the very size that made the A380's wings engineering masterpieces also limited the jet's reach. The 747's wings helped it conquer the world, but the A380's wings became part of its struggle. The 747's wings symbolize balance. Big enough to revolutionize travel, but modest enough to fit the world's infrastructure. They carried astronauts, presidents, and millions of everyday travelers. Eventually, their design went on to inspire countless later jets like the Boeing 777 and even the 787 Dreamliner, which borrowed lessons in efficiency and wing flexibility. The A380's wings symbolize ambition. They were designed not just for today, but for a tomorrow. Airbus was certain would arrive, where airports funneled hundreds more passengers onto each flight, and where bigger always meant better. These wings were sized for the A380-900 that was never built. It was a stretch version that would have carried over 900 travelers across continents. In reality, that demand never materialized. The aviation market shifted, and airlines preferred more fuel-efficient twins like the 787 and A350 that could fly directly between secondary cities. Two sets of wings, one pragmatic, one visionary. One carried the Queen of the Skies for 50 years. The other gave us the largest passenger plane ever built, but one whose time ended too soon. The wings of the A380 and 747 are proof of engineering that's turned into legend. One proved that practical design can endure for generations. Tell us in the comments, which wings impress you more, the timeless 747s or the powerful A380s? If you enjoyed this breakdown, give it a like and subscribe for more. Until next time, keep your eyes on the skies.